Okay, I think that we could start. So, hi everybody, welcome to our seminar Búsqueda de Nueva Física en Aceleradores y el Cosmos. This week we come with the presence of Claudio Gambino. He's a PhD student from the University of Rome, La Sapienza, and he is going to present the talk Rotating Metrics from Scattering Amplitudes in Arbitrary Dimensions. So, please go ahead, Claudio.
Thank you. First of all, thank you for the invitation. It's really a pleasure to give this seminar. And so my name is Claudio Gambino. I'm a PhD student at University of Rome, La Sapienza. And today I'm going to talk about rotating metrics from scattering amplitudes in arbitrary dimensions, which is based on a paper that I'm writing in collaboration with Paolo Pani and Fabio Riccioni, also based in Rome, La Sapienza. So here my outline. So first of all, an introduction. The talk then will be basically divided in two parts. The first part, in which I will discuss some basics of computing scattering amplitudes in the classical limit and how to extract classical objects out of the classical limit of scattering amplitudes. And the second part will be focused on how to interpret certain results in the context of general relativity. So we will start with the basics of canonical quantization of gravity. Then we will see how to recover classical metrics from scattering amplitudes. Then I will discuss how to compute explicitly 3-point classical amplitudes, or basically 3-point amplitudes in the classical limit. Then here we'll finish the first part, and the second part I will start to talk about rotating metrics in general relativity in general, and so what are the differences for stationary spacetime, static spacetimes, and what are the differences between 4 dimensions and arbitrary dimensions. Then I will introduce the protagonist of these talks, that will be the spinning Dress vertex, and then we will talk about rotating metrics extracted from a spin 1 field theory, and then I will define what we call the simplest metric, and then some conclusions. So first of all, it is often said that general relativity and quantum mechanics are incompatible. But to me, the correct statement, or a more appropriate statement, is that quantum field theory that describes the interaction of massless spins through gravitons is non-renormalizable. So in a modern approach, this is not a problem, because we have now accepted the idea of effective field theories. And so we can say that the canonical quantum gravity is just an effective field theory valid up the Planck mass, the Planck scale. Of course, in the strict sense of the idea that we have of quantum gravity, it is useless, because we need a quantum theory of gravity to go beyond to understand what happened at the Planck scale. And so the fact that we can define a coherent quantum gravity theory at below the Planck mass, it is basically equivalent just to the classical theory, or namely the general relativity. So what we can do, what is emerging nowadays, is that just recovering general relativity from the classical limit of this effective field theory can reveal, on one hand, new theoretical structures that are useful for a deeper understanding of a more fundamental theory, and on the other hand, can analytically lead to gravitational observables in a more efficient way with respect to directly solve the Einstein's equation. So here, basically, the story, we have the main topic of general relativity from scattering amplitude, which is something very popular at the moment. And the community basically divides into categories. So on one end, we have these this approach used to compute observables. So people nowadays are trying to evaluate analytic waveforms from coalescence of compact objects, or, for example, scattering of volts. So the turning point is that these kind of processes can be studied in a numerical way with numerical relativity. And with these techniques, we can study these processes also analytically. And on the other hand, we can also do formal computations. So, for example, as we will see, compute the metric starting from a quantum field theory, or, for example, we can also try to understand better the nature of black holes from a double copy perspective, and so on. So, and here there are some review for this story. So let's start considering a minimally coupled theory in arbitrary dimensions, in which the gravitational field interacts with a real mass. So here we have the action, which is this diffeomorphism invariant, and we quantize the gravitational field metric in this way. So a perturbation in a flat background, where k square is just the gravitational coupling constant, so the Newton constant, and h mu nu is the graviton field. So, of course, the theory that we are considering is nonlinear, because we know that gravity is highly nonlinear. And this means that expanding this action in this way, we will obtain an infinite series of terms, every order in k. So, for example, this is the first terms of g mu nu with the upper indices. And this is the expansion of the determinant of the metric. So the idea is to perform this expansion in the action and obtain a field theory in a flat background, in which now the graviton propagates in a flat background and interacts with the massive scalar as any spin to massless particles. So we will have an action with a kinetic term for the graviton, a kinetic term for the massive scalar, and of course an interaction term that we will contain both interaction terms between the massive scalar and the graviton, and self-interaction vertices of the graviton, because of course, since the theory is nonlinear, we will have self-interactions of the field, exactly like it happens in quantum chromodynamics, in which we have the three gluon vertex. Here the story is the same. And then we have to add a gauge fixing term, because gravity is a gauge theory. So what happens is that the quadratic term in the field of the action is non-invertible. And so without a gauge fixing term, we cannot define a propagator. So we have to add it. And we choose a gauge defined in this way, in which this vector f is this one, and this gauge is allows us to continuously move from what is called the Donder gauge, in which alpha is equal to 0, so only this piece survives, to the harmonic gauge, which is very famous in the context of GR, and this happens when alpha is equal to 1. So this piece is vanishing and only this piece remains. But of course, since this parameter alpha is arbitrary, we will obtain quantities that are dependent on this parameter, but it is just a gauge choice. So the advantage of using this gauge is that at second order in the field, the term is independent of alpha. So the propagator, the graviton propagator, have this structure here. So this is the graviton propagator, which is basically the standard one, because in every canonical approach to this kind, this is the standard propagator used for the graviton. So, as I said, now we have a quantum field theory describing the interaction of a scalar field and the graviton field. And since the theory is nonlinear, we have all these kind of interactions. So we have an infinite number of vertices with an infinite number of gravitons attached to them. So we will have the 3 graviton vertex, the 4 graviton vertex, the 5 graviton vertex, and so on, as well as the interaction vertices. And among them, there is one which is very important, and is this one. So the three linear vertex that couples two massive scalars to one graviton is, as any gauge theory, this vertex couples the gauge field with its current. So in this case, the current of the interaction is the energy momentum tensor. And so we will see how this relation is really important. So at this point, this is the framework, and we make a step back, and now we want to find a way to relate an amplitude calculation to a classical quantity, like the metric, for example. So here the Einstein equation, so the equation that contains the metric, and here the T mu nu is the energy momentum tensor that I wrote before. So in this case, T mu nu is really the current of the gravitational interaction in the action that I wrote before. So here we will expand the metric in what is called a Post-Minkowskian expansion. So we have the metric, which is expanded in terms of flat background and a graviton field. And the graviton field, which is, let's say, just the metric perturbation, but is not an approximation, is this relation is exact. The graviton field will be expanded in this Post-Minkowskian expansion, in which the index n count the powers of the Newton constant in this expansion. So, for example, H1 will be the term proportional to G, H2 will be the term proportional to G squared, and so on. And this will we will see that this is equivalent to a long-range expansion, so an 1/r expansion of the metric. So what we do is that we replace this expansion inside the Einstein's equations, and we will obtain on the left-hand side terms that are Hn, and terms that are, for example, H1 square, H2 square, and so on. And these are basically the self-interaction term gravity, because we know that the famous sentence that gravity gravitates. So the energy momentum tensor of the full theory will contain also self-interaction terms of gravity. So we can rearrange the Einstein's equations in this form, in which now T0 is exactly the energy momentum tensor of the matter source, and Tn will contain self-interactions of gravity. So once we have the Einstein's equation written in this form, we can integrate, and then we can obtain the metric written in terms of a Fourier transform of the energy momentum tensor. So basically, this is just rewriting of the Einstein's equation. And it is important to notice that in all this thought, we will consider stationary metric. So we will consider a space-time which is explicitly independent by time, on time. So the time derivative of the field is 0, and therefore Q, the variable over which we are Fourier transforming, its time component is 0. So it holds this relation, and this allows us to write the Fourier transform not over all the space-time dimensions, but over only the spatial dimension. So this is something which will be recurrent in the talk, and I will often referring to spatial dimensions indicating this small d. So for example, in 4 space-time dimensions, the space dimension, of course, there will be 3. So the idea now that we have rewritten the Einstein's equations in this form, the idea now is to compute the energy momentum tensor that appear here in terms of scattering amplitudes. So this is the idea. And the relation, of course, will be that the energy momentum tensor is related to a process like this, in which a scalar probe emits a graviton. So we have to see how to compute 3-point amplitudes like this in the classical limit. First of all, is important to set the types of the approximation that we are making, because we have to define what we mean by classical limit. First of all, since we are in an effective field theory framework, we have only access to long-range gravity. It means that from a quantum field theory perspective, that we have access only to the low energy limit of the theory. Since the scale of this effective field theory is the mass Planck, it means that Q, that will be the transferred momentum of the scalar or the momentum of the graviton in general. So that Q must be much smaller than the Planck mass, and the Planck mass will be much smaller than m, which is the mass of the scalar. The scalar, which is at this level just a scalar particle, at the end of the story will be an extended object. So what in this context is just a particle, at the end when we will compute the metric, m will be, I don't know, the mass of the black hole. So of course m is bigger than the Planck mass. So this is the important relation to keep in mind. And this is different to account for the classical limit. So that is the limit in which we send h bar goes to zero, h bar that goes to zero. And because of course we can define quantum correction that are long range. So the two approximations are not the same. And it is very important to notice that, unlike the common saying, by which classical physics here is recovered only by three-level processes, in gravity, loop amplitudes are classical. So this is first observed by Iwasaki in the 71. And basically the idea is that if you think about the only other long-range force that we know, which is electromagnetism, in QED, if you want to recover classical electromagnetism, you can just observe what happens at tree level. So in QED, every loop amplitude is a quantum process. In gravity, it's different because gravity is a self-interacting theory, while the electromagnetism is not. So we can see this phenomenon happen here. And in particular, let's see why the argument in which loop amplitudes are powers in h bar is wrong. So if we consider a generic amplitude at L loops, so imagine that the amplitude will have P propagators and B bursts. So the standard argument says that the propagators go like h bar, while the vertices go like 1 over h bar, just because the propagator is the inverse of the action in some sense. And then an amplitude with P propagators and B vertices will go like h bar to the L minus 1. So we can rewrite it in the end, factoring out 1 over h bar. We can say that the tree level is classical, the one loop is the leading order quantum correction, and so on. So this is the standard argument. However, in the low energy limit, so if we consider first the low energy limit and then make this argument, we can see that internal massive lines and massless lines behave differently. So in this approach, when we write a propagator, we are not saying if it's a propagator of a massive particle or a massless particle. Let's see what happens if instead we consider this difference. First of all, for restoring the h bar in a theory, we can use the K-Mock approach, which is just a recipe that tells you that at operatorial level, we can just restore the h bar in the theory just by sending the massless momentum to h bar q, and every spin in the theory send it to 1 over h bar. So this is the recipe for reinserting back the h bars in the theory. And we can see, for example, on massive propagator. So this is the h bar denominator, which is this one, and then q that goes in h bar q. So p square, of course, goes away with m square, and at this point, we have q square h bar square and p dot q h bar. Of course, if we recall this low energy limit, we have that q is way smaller than m, and of course p. So q is smaller than p, and so q square is subleading with respect to p dot q. The only piece which is left is p dot q, and the h bar cancels. So at the end of the day, the massive propagator in the low energy limit is independent of this h bar. This means that if we want to account for the h bar dependence in a scattering amplitude, we have to make a distinction if the propagator is massive or massless. So here we have two amplitudes. And if we perform this counting, we can see that this amplitude goes like this, and this amplitude goes like this. So we can see that this amplitude is classical for the expansion that I wrote before, while this amplitude is quantum. Of course, classical in the sense that the lowest order in the energy expansion is classical. Of course, this amplitude will have quantum contribution, but the lowest order in energy is classical, while the lowest order in energy expansion of this amplitude is quantum. So this amplitude in its entirety, when h bar goes to 0, is vanishing, while this amplitude is not. So this tells us that loop scattering amplitude with an internal free structure, and I will add that with a specific topology with massive propagators, are classical. And this tells us that these post-Minkowskian expansion, so these expansion of classical quantities in the Newton constant, can be related to the loop expansion, because of course loop expansion is an expansion in the coupling constant of the theory, and in this case is the Newton constant. So we can say that the post-Minkowskian order of a classical quantity is the number of loops plus 1. So we will see that level amplitude will lead to 1 p.m. Order of the classical objects. One loop will lead to 2 p.m. and so on. So let's see explicitly how this works. Here the linear vertex, the vertex that couples two massive scalars and one graviton, and this is written in terms of its current, which is T mu 0 in the sense that is the matter source. So here, this is the quantum vertex, so the complete vertex of two scalars and one graviton. And now we have to write this vertex in the classical limit. So if we impose stationarity, and so stationarity means that Q, the temporal component of Q is 0, and we impose classical limit so that we only care about h bar to the 0 powers. This is the expression of the vertex. So this is the vertex in the classical limit. When I say classical limit, I mean h bar goes to 0, low energy, and so on. So this is the vertex, and we can compute the energy momentum tensor at this level just by this equality here. We will find this. So this is, of course, the energy momentum tensor of a point-like particle sitting in the origin. And just by replacing this in the Einstein's equation, we can recover the metric at 1 p.m. So the leading order contribution of the metric. And we will see explicit formulas later. This is just but the Schwarzschild metric. Of course, we are considering a metric of a point-like particle, and we recovered the Schwarzschild metric. And to do this calculation, we have just to notice that this Fourier transform here with this definition of rho, which is the harmonic function in arbitrary dimension. So, of course, at tree level is trivial. Let's see what happens at one loop. So how we compute an amplitude like this. So this is just by reading the amplitude, the two vertices and the graviton propagator and the three graviton vertex. And what we have to do is to impose the classical limit at the beginning of the calculation. So this is something very standard in this kind of calculation. And the idea is that you will have a simplification in the calculation if you impose the classical limit at the early stages. So we don't do a full quantum computation and then take the classical limit because it's very complicated. But instead, we perform the classical limit at the beginning. So in a way that at the end, the result is already classical, is already what we want. So taking this expression, we have to impose the low energy limit, the classical limit, and the stationary limit. And the results of these limits, we can integrate out the temporal component of the loop momentum, and we can sum directly over all the topologies of the diagram. Of course, in this case, trivial because we have only one topology. But for example, a two loop, you have more topologies. But basically, at the classical level, they are all the same. And this is the result. So this is the proper way to write the amplitude if you are interested in the classical limit. So you see that we're now integrating over small d, and of course now we have to deal with this numerator, with this tensorial contraction, and we compute this integral with loop integrals reduction techniques. So for example, consider an integral like if I replace the loop momentum, if I shift the loop momentum in this way, I will obtain a denominator which is even for L that goes in minus L, and the numerator will be this one. And of course, by parity, these terms vanish, and we are left only with this. And defining this L loop sunset master integral in this way, we can see that this integral here is just one over two of this J1. So this JL is the master integral which defines the proper way to describe the amplitude at L loop. And since at the end of the day, we are not interested in explicitly in the stress energy tensor, we are interested in the metric. And we know that the metric is the Fourier transform of it. So at the end of the day, we are interested in the Fourier transform of this object. So, and despite the fact that exists an explicit expression for this object, we're only interested in the fact that exists an explicit Fourier transform, which is this one. So you see that at one loop, what we have, for example, is J1, and in Fourier transform in J1, we will obtain rho to the second power, which is the next order of the expansion of the metric. By the way, you can interrupt me anytime for any questions. So this is the explicit result for the one loop amplitude. So this is the stress energy tensor. You see an explicit dependence of the parameter alpha, which is just a gauge parameter. You see that on the entire amplitude, the master integral factor out. And of course, we have some power of k, which is just the gravitational coupling constant. So Fourier transforming this quantity, we obtain the metric. So this is the metric in the harmonic gauge, and later we will argue that again, this is the second order expansion of what is called the Schwarzschild-Tangerlini metric, which is the static metric, which is the metric of a static object which is spherically symmetric, and so this is the expression. And of course, we can generalize this argument at any loop, and just by noticing that at every loop order we have this relation here. So for every loop order, the amplitude will factor throughout a master integral like this. And just by noticing that we know this master integral Fourier transform, for every loop order, we have this kind of expression here. So of course, depending on some tensorial structure and so on, but this is the how the metric will depend on powers of 1 over r, because remember the definition of rho is it's just some power of 1 over r. So for example, in 3 spatial dimensions, rho is just 1 over r. So we have that at 3 level, so h1 goes like 1 over r. The metric goes like 1 over r square, and so on, in 3 dimensions, in 3 spatial dimensions. This is completely generic, and you can see here a formal expression of the L loop amplitude, in which this one is a combinatorial factor that take into account the different way in which we can arrange the graviton legs to the massive line. And so basically, if you want to compute a L loop amplitude, you just have to care about this object here, so that enters in this expression. And so, as I say, this one leads to what is called the Schwarzschild-Tangerlini metric, which is the only solution that you have in general relativity for describe a static matter source. And okay, so this is how the story goes for computing scattering amplitudes. I know that this is not exhaustive, but this is basically how you can compute scattering amplitudes in the classical limit. Of course, this is related only on 3-point amplitudes, in which you compute the emission of a graviton from a source. Of course, the story is different if you want to compute 2-to-2 scattering amplitude and so on. But for what concerns these talks, this is enough. And so let's start to interpret these results in terms of general relativity, and what these formalists can tell us. What can tell us about new results in general relativity? So first of all, we have considered a scalar field up to this moment, and we have seen that. I mean, we didn't have seen explicitly, but I can tell you that this scalar field leads to the Schwarzschild-Tangerlini metric. So basically, we have proved that considering a point-like particle, which is spinless, this corresponds to a static source sitting in the origin that generates a spacetime. And in general relativity, there exists a theorem which is called the Birkhoff theorem, that states that any spherically symmetric static spacetime is described by this metric. So the results that we have obtained is in a certain way expected, because we have obtained the only thing we could, the Schwarzschild-Tangerlini metric. However, in considering the spin, so starting to considering rotating objects, the story is very different, because if we now, the difference between static and stationary is crucial, because static is something which is not time dependent and is also not rotating. So the mixed temporal part of the metric is vanishing. On the contrary, stationary means something that is independent by time, but is rotating. So, and if we consider only stationary spacetime, so if we allow rotation, there is no more such theorem. And what happens is that outside, for example, a star, I mean, we know that in general relativity, the only black hole solution is the Kerr solution, is the Kerr black hole. And differently from the scalar case, outside a star or whatever rotating object, the solution is not Kerr. So there is no theorem that guarantees us that the solution outside of a rotating object is unique, as was in the scalar case. So what I'm trying to say is that before we computed the metric from a scalar particle, and the only thing we could have is the Schwarzschild-Angellini metric. Now it's different, because if we compute the metric from a spinning particles, we don't know actually the metric that we are ending with, because there is no uniqueness theorem for spinning metrics. And in and this is for only for 4 dimension, and in arbitrary dimension is more complicated, because there is no uniqueness even for black holes. So while in 4 dimension, curved black holes are the only black solution, so the only exact space-times with an horizon, in arbitrary dimension is not the case, and we can find many exact solutions which have an horizon. So the question is, how can we capture all this phenomenology to scattering amplitudes? So the answer, in a certain way, is these spinning vertices. So first of all, let's consider a spinous particle coupled to gravity. So before we have considered a scalar field, now we consider a spinous field coupled to gravity. Of course, this spinous field will have an interaction vertex, and as we have seen, the only vertex that we need is this one. The other vertices that we need are the self-interaction graviton vertices in order to compute the scattering amplitudes. But the only vertex that we need that accounts the interaction between the massive fields and the graviton is the trilinear one, which is this one. And now this vertex will have some spin indices that will depend on the particular representation of the Lorentz group of the field. So for example, if I consider a spin 1/2 particle, A and B will be spinor indices. For a spin 1 particle, A and B will be Lorentz indices, and so on. And so the relation between the source of the matter field and this 3-level vertex is this one, in which we put on shell the external massive states, and we keep off shell graviton here. And here this epsilon takes into account for bosons and fermions, because they have a different mass dimension. So it's a technicality, but the important expression is this one. So how T mu nu is related to this vertex, and moreover, now we have to also to think how to take the classical limit of the external state, because before we had a scalar particle and we had no external state because we had no polarizations. Now we have polarization, so we have to take into account the classical limit of these objects, and we define it just in this way. So since in this context is the transparent momentum of the particles, so is P1 minus P2, from the same approach that I briefly told you before, we can expand it in powers of h bar and just say that the polarization state P2 is equal to the polarization states of the two particles is equal up to quantum correction. So up to quantum corrections, we can say the, and start from these brackets, we can expand it in the classical limit. So we have P1 up to quantum correction, and then define the Dress vertex. So the Dress vertex is the vertex of a spinous theory, which where we put on shell the external states considering inside the classical limit. So here is the definition of the Dress vertex. And so the question now is, who is this guy here? Less. And of course, this is a spinning particle. We want to recover, let's say, a metric that takes into account the angular momentum of the spacetime. So in the Dress vertex, S, capital S, stands for the classical spin of the particle, which will become the angular momentum of the object we are mimicking. So capital S is the, let's say, is the classical angular momentum of the object. The question is how can we recover it from the quantum expression of the vertex, because we start from a quantum expression of the vertex, and the idea is to express the vertex in terms of the generators of the Lorentz group, and then take the classical limit by putting the vertex in a bracket between the states. Basically is the definition of S. So we define the angular momentum of the object as the classical limit of the Lorentz generator of the particle, where in this case C is just a normalization depending on the representation. So spinors, so spin 1 half, spin 1 have different normalization of the states. So, but this is the important relation. So the definition of what is the angular momentum. And of course, it's important to notice that S mu nu is an antisymmetric spin tensor, which is stationary as the transferred momentum. So S0 mu is 0. And only in 4 dimension, we can write the usual expression in which we relate the spin tensor to a spin vector. Because it's crucial to notice that in arbitrary dimension, the angular momentum is not a vector, but is a tensor. And this is related to the rotational group in arbitrary dimension. So the group of the rotation in arbitrary dimension is SOD, small d, and the fact that the angular momentum is a vector in 3 dimensions is just an accident by the fact that the adjoint representation of the group coincide with the dimension of the group and with the fundamental representation, let's say. But in arbitrary dimension doesn't happen. So angular momentum is actually a tensor, an antisymmetric tensor. And we will see how this is very interesting from phenomenological in quotes point of view, because, for example, black holes in 5 dimensions, so black holes in d small equal to 4, have 2 dependent angular momentum. So we will see this. So one point is that, okay, but we have spent half an hour to talk about scalar amplitudes, and now we are talking about spinning amplitudes. And here we can prove that through this definition of dressed vertex, basically a spinning amplitude is formally equivalent to a scalar one. Because if you consider the massive line here, you have the bracket between the states, and then we have the vertices, propagator. Of course, the propagator of the massive particle will depend on the representation of the. But if the particle is massive, and it is, we can decompose the numerator of the massive propagator in this way, and at this point we have that up to quantum corrections, and imposing the classical limit, we can recover this expression. So basically, we have decomposed the full massive line here, that in general, at the quantum level, depends on the specific representation, but at the classical level, we can prove that it's just a product of dressed vertices. So the whole spin dependency is inside the dress vertex and not in the amplitude structure. So we can use all the machinery we have already discussed before in order to compute spinning amplitude. So now the external states have some spin, and of course we are considering the same field, so the spin is the same, and this is basically the exact same expression that I wrote before, with the difference that now the vertex is dress vertex. So we'll have some angular momentum dependence inside. And it's important to notice that in all this story, there is a guiding principle that guides us, which is called spin universality. Spin universality basically tells us that if we compute the dress vertex in a field, this will reproduce, I don't know, the metric of a rotating object up to order S. So this is more complicated to write it than to understand it. I mean, if I consider a spin 1 field, I can construct only things up to the second order in the angular momentum. If I consider a spin 1 half field, I construct things only up to linear order in the angular momentum. So this is the relation. This is the spin of the particle, and this is the angular momentum of the object. So, for example, a massive spin 2 field will reconstruct a classical object up to the 4 power of angular momentum, of the classical angular momentum. And if I consider a spinous field and I build a classical quantity in this way, if I do the same with a lower spin theory, the results is the same. So every lower order spin are the same, must coincide. This means that if I compute the linear order in the angular momentum of a classical quantity with a spin 1 half theory, or with a spin 1 theory, or with a spin 200 theory, the linear order is the same. It must be the same, because what I'm doing here is just is just a technique for the computation. So the result is independent. And so we can expand our classical object, in this case the metric, but we can do it for every classical objects you want, in this multiple expansion. So n counts the powers of g, of the Newton constant, and j counts the powers of the angular momentum. So h 1, 0 is the scalar term order g. h1, 1 the order g and linear in the angular momentum of the object. Or so can be a black hole, can be a neutron star, can be whatever you want. So now this is the general story, and let's see what happened for the specific case of spin 1 theory. Now, here there is this warning here, because we are talking about spinous particles in arbitrary dimension, and it can be tricky, because the way in which we catalog the particles is depend on the structure of the Lorentz group in 4 dimensions. But in arbitrary dimension, the structure of the Lorentz group is more complicated, and there is not only one quantum number to catalog the particles, and so the story is more complicated. And so for simplicity, when I say spin 1 particle, I'm just referring to vector fields, so fields with a Lorentz index. So consider a minimally coupled gravity theory, a field minimally coupled to gravity, which is a vector and is called Proca field. So the Proca field is just this guy here. And of course, considering I forgot to the pure gravitational piece. And we can do the same as before for the scalar vertex. So action here will lead to a vertex like this, the trilinear vertex. And this trilinear vertex, we have a quantum structure, whatever it is, but we are only interested in the classical limit of it, which is this one. So this is the trilinear vertex in the classical limit. And we can see the scalar part, because it's independent on the angular momentum. The angular momentum is this tensor S here. Then we have the dipole term, because it's linear in the angular momentum. And then we have the quadruple term, because it's go like S squared. Now, what I said before, the spin universality, what it means? It means that the scalar term is exactly what we recovered before with the scalar theory. So if I compute this vertex for a spin 2 massive particle, I will obtain more pieces here, because I have access to higher powers in the angular momentum, but the terms that I wrote here will be just the same. This is the idea of spin universality. And I collected here the idea. So the scalar part is we consider as S equals 0 theory, and then the scalar and dipole would be the same, consider as spin 1/2 theory, and so on. And so this is the what I call the minimal address vertex, because it's associated to a minimally coupled theory. And however, if we consider a non-minimally coupled theory. So this is the question. And I did not say anything about it in the scalar case, because one can prove that in the scalar case, the scenario is very trivial, and actually the non-minimally coupled action is just introduce gauge redundancy. So it's physically equivalent to a minimally coupled theory. But in this case, it is very different. So let's see what happens if we consider a non-minimally coupled theory. So we can build a non-minimal operators in the action with an explicit spin dependency. And we can define this tensor here with a well-defined covariant antisymmetric tensor, such that at the first order in the gravitational coupling, its limit is the classical angular momentum. So this is a covariant operator in the sense that it's covariant with respect to the whole background, and this is covariant just in the flat background. So this is only at first order in K. We can write the most generic action this way. So we will have terms that are S to the 0. Then one can prove that there are no terms linear in the spin, and we have several terms quadratic in the spins, like this one. We'll have in total 6 terms. Of course, we can write many other things, but one can prove that everything you can write except this is just redundant or quantum contributions, or we don't care. So this is, for our purposes, the most generic action. And what we can do is that you can see that some of these coefficients here are dimensionful because we have extra derivatives here. We can redefine those coefficients, those coupling constant in terms of dimensionless coefficients, and then we can obtain the most generic trilinear vertex associated with the most generic non-minimal theory. So this is the vertex that couples two massive vector. And you can see that it depends on several coefficients. So in particular, 4 coefficients. Now these 2 terms are independent of anything which is arbitrary, because as we have seen, the scalar part is universal in general relativity. So the scalar part of the metric is universal. So every metric in general relativity have the same scalar part, and this also happens to the dipole term of any metric. So if you take any metric in GR, which is describing rotating spacetime, and you expand it at first order in the angular momentum, that order is universal forever. So it's good that we have no coefficients here, but here we have several coefficients here. And basically what we are computing here is the energy momentum tensor of the most generic stationary spherical symmetric method distribution as quadruple hole. So if I take a matter distribution in spacetime, the most generic thing I can make is this one at this order in the angular momentum. And sorry. And another things that we can check, for example, is that this action is this energy momentum tensor is conserved up to terms that vanishing in the when we perform the Fourier transform, because the T mu nu is conserved. And it is very important to notice this thing that we see that here we are just writing T mu nu in terms of a bunch of tensors. So at our disposal, we have only the mass, we have the transfer momentum Q, and we have the spin tensor, and we have the delta as a tensorial structure. So one could say, okay, I can build this energy momentum tensor just by considering the most generic symmetric tensor that I can build with this object. And of course, this can be done. So write the exact same thing, completely forgetting about the amplitude approach and the quantum field theory underlying this thing. But the catch is that now that I have a quantum field theory to relate this vertex, I can tell you what is the minimally coupled vertex. And I can tell you what is the vertex associated to the minimally coupled theory. And this is something very important for what we are going to say. So you can see that this is the most generic vertex, and this is the vertex associated to a minimally coupled theory. So now that we have this vertex at our disposal, we can compute the metric, and just a few words. We can. There is, in fact, another vertex, let's say, which have this form, and however, this vertex doesn't contribute to the physics of the problem. It's just introduces a gauge redundancy in the problem, so we can completely neglect this for our discussion. And as I said, we can insert back the energy momentum tensor in the essence equations and obtain the metric. So we have the metric of the scalar part. So you see that there is no angular momentum here. And at this order, the metric is universal. So is the only thing I can have. At dipole order, we have only the current piece here. And again, this term is universal, so there are no other choices that I can. There are no other things that I can make. However, the interesting part is a quadruple order, because at quadruple order we obtain this metric here, that of course will depend on the same coefficients as before. So we see that. So this is the temporal component. Everything here is quadratic in the angular momentum S. And the mixed component is 0, as we expect, because we expect for symmetry reasons that here this part of the metric will have only odd powers of the angular momentum. And as I said, I can compute the so this is the most generic metric at this order, but I can relate it to the minimal limit, so the limit in which the quantum field theory is minimally coupled, by choosing the coefficients in this way. So and we will see what this means. So just by saying that we have to ask ourselves, what is the interpretation of this free coefficient? Because this is these are free numerical coefficients. So what is their interpretation? And one can actually show that the C's are just gauge artifact coefficients. So tuning the value of the C1 and C2 is just a gauge choice. So the contribute of the C's can be absorbed with a coordinate transformation, while the contribution of the H's is a physical one. So the H's cannot be reabsorbed by a coordinate transformation. It means that the value of the H's will in fact model the structure of the matter distribution, of the matter source that generates the metric. So choosing a different H1 and H2, it means consider a different source that generates the space. In other words, choose a value of H1 and H2 will lead to different solution of the Einstein's equation. So, for example, I can expect a black hole to have a fixed value of H1, H2, and another solution to have different values. Here, okay, so this is ours, and let's see how to interpret these results. So the important thing, I mean, one of the important things is that this metric is, of course, well-defined in arbitrary dimensions. And what we can say, now in GR, there is what is called the Thorne formalism, which provides a framework in which we can read the quadruple moments of a space-time. So it means that a space-time can be divided into quadruple moments. And this is exactly the same when we studied in school about electromagnetism. So if you think about distribution of electric charges, the electric field out of it can be decomposed in multiple moments of the electric field. In general relativity, is the same. We can decompose our space-time in multiple moments, and each multiple we specify how our space-time is made of. And Thor in the 80s gave us a formalism to read these multiple moments. And the original formalism of Thor was based in 4 dimensions. And very, very recently, last December, came out a paper by Heinen and Meyerson, which extends this formalism to 5 space-time dimensions. So, because, I mean, it's actually a very hard formalism to make it consistent, because you have to prove that your quadruple moments are gauge invariants in a certain way, that they do not depend on the reference frame. So last December, this paper proved that it is possible to extend the Thorne formalism in 5 dimensions. But what we did here, the quadruple moment, not only in 4 and 5 dimensions, but in any dimension. And if we conjecture that is in these ACMC coordinates, where it stands for asymptotically Cartesian mass-centered coordinates. So if we conjecture that in our coordinates, we can actually read the multiples, from the Thorne prescription, the mass quadruple is this one. We have defined the mass quadruple in arbitrary dimension beyond 4 and 5 dimensions, but we did something more, which is something astonishing when we saw this for the first time, because we saw that there is another multiple moment in the metric that was not found in this paper by Heinen. So basically what they did is to work of Thor and extend it to 5 dimensions. And in the work of Thor, he says that you can read the multiple moment. For example, you can read the current moments by reading the leading terms in H0i, and you can read the mass moments by reading H00. So in the Thorne formalism, the spatial part of the metric is completely negligible in order to extract the multiple of the space-time. What we found is that actually the space-time component of the metric defines a new multiple moment of the metric. So what we found is that, I will tell you this later, but in the next slide, but basically what happens is that in 4 dimensions, by an accident, and we already saw this accident because the fact that I can write the spin tensor in terms of a spin vector is a clue that in 4 dimensions, there is some accident that simplifies the story. And in fact, in 4 dimensions, there is this accident that makes only one of the quadruple independent. So only a combination of the two quadruples. So, M2 and M2 prime, only a combination of the two are physical, I mean, is independent. But in 5 dimensions and beyond, so when the space-time dimension is greater than 4, the M2 and M2 prime are independent. So we have 2 multiple moments. And we will see that it's crucial, this fact, in order to reproduce exact solutions. So the final step, the final thing that I will discuss is the fact that we have proved our metric. We have proved our metric by reproducing some exact solutions. So, for example, we have took in 4 dimensions what is called the Hartle-Thor metric, which is the metric that gave to us the most generic space-time at quadruple order, and was introduced by Hartle-Thor in order to describe the metric of a neutron star originally. Now we can see here what is the explicit form of the spin tensor, because the spin tensor we can diagonalize it. We can diagonalize it in this way. So this choice of the spin tensor basically is equivalent to choose the angular momentum of the black hole along the z-axis. And from the Hartle-Thor formalism, we can see that if we take the G00 part of the metric, the mass quadruple is this one. Oops, is this one. And we can compare this result, our result, and we find that the mass quadruple of the Hartle-Thor metric is actually H1 plus H2. So this is the mass quadruple of Hartle-Thor in our formalism. And the very important fact here is the fact that we have an underlying quantum field theory in this description. So we know what is the minimal limit, in the sense the metric associated with the minimally coupled action. So in the Hartle-Thor formalism, when M2HT is equal to 1, the metric is the metric of a Kerr black. And so we can see that if we take the minimally coupled limit, we actually reproduce exactly a Kerr black hole. So this is a crucial point. And so the crucial point is that a Kerr black hole is compatible with the minimal solution. So I go some slide back because it's an important point. So if I take an action like this, minimally coupled action, and I have a vertex like this, when you can see that is way more simpler than this one. This vertex here reproduce a Kerr black hole. In 4-dimensional Kerr black hole, the only black hole I can reproduce, because it's the only black hole that exists. But it's not trivial that minimally coupled theory reproduce a black hole. What we're saying here is that in 4 dimensions, a minimally coupled quantum field theory reproduces a black hole. So a non-minimally coupled theory is not a black hole, it's something else, it's a star, it's a neutron star. So we did this check and it worked, and we can go further and, for example, try our metric. I mean, take our metric and reproduce the exact solution of the so-called Myers-Berry black holes in 5 dimensions. So the exact solution of these black holes is this one. So this is a black hole in 5 dimensions. And here you can see that what I briefly said before, that in 5 dimensions, the group of spatial rotation is SO4. So we have 2 independent angular momenta. And this is important because now we have to separate the spin tensor in this way. So this is a sort of diagonalization of the matrix. In some sense, we choose the angular momentum to be orthogonal to some planes. And So again, it's important to notice that in this case, we have two independent angular momenta. And the question is really simple. I mean, with this metric here, I can tune the parameters in order to have that metric, in order to reproduce Myers-Berry black holes. This is the question. And the answer is yes, if you tune the parameters in this way. But you can see that these are not the minimal limit of the parameters, because the minimal limit is when H1 is 1 and H2 is 0. So what I'm saying here is that the minimal what I call the simplest metric, so the metric associated with the minimally coupled theory, is not a Myers-Berry black hole, while black holes are the closest things to Kerr black holes that we can build in arbitrary dimension. So so this is the fact. So the Myers-Berry black holes is reproduced by our metric, but does not coincide with the simplest metric. So here I define what I call the simplest metric. So the metric where H1 is 0, H1 is 1 and H2 is 0. And I already said that the C's are just a gauge redundancy. So it's just a choice of reference frame, it doesn't matter. And this is the simplest metric. So this is the metric generated by a quantum field theory minimally coupled to gravity. So we have seen that in 4 dimensions, this reproduces the Kerr metric. So in 4 dimensions, the simplest metric is a black hole, but in 5 dimensions is not. And I did the example of Myers-Berry black holes. We know other solutions. For example, we know black ring solution, black Saturn solution, and none of them coincide with the simplest metric. So in dimension greater than 4, there is no known solution that matches the metric. So the question is, since we know that in D equal 4, the black holes are the simplest object, is this true in higher dimension? This is the question, and the answer is I don't know, and nobody knows. So yeah, so this concludes the talk. So here are my conclusions, and to resume what we have seen is that we have derived the EMT of the most generic spherically symmetric stationary method distribution of possible order in arbitrary dimension. And I repeat, this is something that it doesn't that can be done without a quantum field theory, but to have what is crucial. I mean, to have a quantum field theory is crucial to say that we have computed the metric induced by such current and proved that in V greater than 4 there exists 2 independent quadruple moments. So this is an important result. So one of the 2 important results is this, that we have proved the existence of a new multiple moment in the metric for higher dimension metrics, and that the simplest configuration of the source does not coincide with any known solutions of the Einstein equation in higher dimension. So further direction are: it is possible to find the simplest exact solution in higher dimensions. Does it exist? And of course, it is a black hole because it is not trivial that, first of all, it's not trivial that such solution exists. And second, if exists such solution, maybe not a black hole, some other solution. And of course, another question is, what is the multiple structure in arbitrary dimension beyond the quadruple order? So I did everything up to second order in the angular momentum. And what is the structure at higher order in angular momentum? So S cube, S to the 4, and so on. And finally, this is a more tricky point, but something about it. We have considered a spin one field in the meaning that we consider a vector field. As already said, the structure of the Lorentz group is richer in higher dimension. So there exist fields with a mixed, with a mixed representation. So I can mix spinor indices and vector indices to build fields with a mixed representation. And what in my understanding is that with a spin one, so with a vector field, I have classical physics at quadruple order. If I consider a spin two field in the sense of the standard sense, I expect to have classical physics as at s to the 4. But what happens if I consider a field in a mixed representation? So which is not spin one, is not spin two, is something different because I'm in arbitrary dimension. So I'm in a case in which does not exist the limit in which d is equal to 4, and it will be very interesting to see what happened in this case. So this concludes my talk, and thank you very much for the attention.
Thank you so much, Claudio. So please, we could pass to the questions. So if someone have a question, please open the microphone.
I have a question about this future directions. So like if nobody knows what is like the simplest exact solution, or if it even exists, what would be like a principle to follow, or like a direction to find out if it exists, and then compare it to a black hole?
Yeah, yeah. I mean, I don't know. The honest answer is that I don't know, because there are no. First of all, there are no guiding principle to build exact solution in general relativity. So, I mean, we have some exact solution in 5 dimensions. For example, as I said, we have these Myers-Berry black holes, black rings, black Saturns, but there are just 3 or 4 solutions, and that's it. So nobody have found any more solution than this, and these are not the simplest solutions in this sense. So what I think is that since Kerr black holes are the simplest solution, I expect that this higher dimension simple solution will be very similar to Kerr. But it's something that confused me, because Myers-Berry black holes are the direct generalization of Kerr. So Myers-Berry are really, really close to Kerr, and they are not the simple solution. So going back to your question, if it exists a principle to find this exact solution, there is not such principle. So yeah, it's very tricky business.
Thank you, and thank you for the nice talk.
Thank you.
Okay, anyone else? I noticed that Carlos have a question. Well, go ahead, Jorge, please.
Hello, I have a question. This formalism works fine with massless. Is there a way to use this scattering amplitude with?
I have trouble to hear the question.
Yes, me too. Actually, okay, we can wait. So, Carlos, could you want to express your questions? Well, I'm going to read because we have a form, and he mentioned how the term formalism construct the default metric.
Sorry, how then?
It mentioned how the term formalism construct the default metric.
Okay, so go back. So here I said, I mean, in these two slides, there are two different things. So one thing is the Hartle-Thorne metric, which is just the most generic metric, which is exact in G and is valid up to the square of the angular momentum. So it's valid only up to quadruple moment. So this is the Hartle-Thorne metric. And the Thorne formalism to define the quadruples, it basically is defined in this way. So in this formalism, you define this set of coordinates. We again are asymptotically Cartesian mass-centered. So, and in fact, these are exactly the coordinates we are using. So, which are Cartesian, asymptotically flat, and mass-centered. So the source must be centered at the origin. And you have to define these coordinates in such a way that you expand the metric. And in particular, in this formalism, you are only interested in the 0,0 part of the metric and the 0i part of the metric. From the 0,0 part of the metric, you can read out the mass multiple. From the 0i part of the metric, you can read out the current multiples. And the way in which you can read these multiples is that basically you define a metric expanding the metric in some power of 1 over r, and a certain order, you know how to build how the multiple enters. So for example, the quadruple moment enters in terms in which G00 goes like n2 over r square with some dependency of the angular variables, because the Thorne formalism can be formulated both in Cartesian coordinates like these ones or in polar coordinates.
Sorry. Okay. And so yes. So I define this way. So you define this set of coordinates, and you basically define your multiples, and you prove it that are independent by the choice of coordinates within this ACMC gauge. I don't know if this answer to the question.
Okay,
and in 5 dimension is the same. So is exactly the same. The only thing that changes is the dependency of the radial function, because as I showed at the very beginning, the harmonic function depends on the so in fact you can see that in D equal 3 we have 1 over r, while the leading order, while rho in higher dimension is different. So this is the only thing that changes in the Meyerson formalism, but the idea is thus the Thorne one.
Okay, thank you so much. Anyone with questions? Go ahead, Jonathan.
Hi, Claudio. Nice talk.
Thank you.
My question is, what mathematical package are you using to calculate loops to loop order?
Okay, very good, because I forgot to mention. And okay, here. So this is just a sketch of the idea of loop integral reduction. So this is a very simple example at one loop, and you can find basically all the reduction formulas that you need to compute the full one loop amplitude by hand. Already at 2 two loops, the story is way more involved. So you cannot do this game by hand, and you have to use Mathematica. So there is a package that I use, for example, for this kind of calculation, which is called LightRed, and it stands for loop integral reduction formula. So it's a standard package of Mathematica. It is called LightRed, and it basically works that that you define a space, a vector space in which you put your momenta. So, for example, in this case, you will put U, which is the transfer momentum, and L, which is the loop momentum, in this vector space.
Yes.
And this package will find the master integrals. So we'll find automatically these master integrals J. And so whatever integrals you put in, the package will give to you this kind of expression. So something that is rewritten in terms of master integrals, basically. So the package is LightRed of Mathematica. But there are many others with many techniques. I mean, the core idea of these things is the IBP relations, so the integration by parts relations in loop integrals. This is the basic idea, and then there are a lot of packages using this idea to compute this kind of integrals.
Okay, thank you. And also, I have the question of Jorge. Jorge, this formalism works fine with massless particles. Is there a way to use scattering amplitudes with mass particles?
Okay, I mean the basic idea is that we are recovering a classical limit of a theory. Okay, so in this case we are recovering the classical limit of general relativity, but just because I'm considering this term. Okay, so I can consider also different theories with respect to general relativity just by changing the terms, which is per gravity. But the fact is that I'm considering gravity, and gravity is an interaction which is a long range, and in order to have such an interaction, these must be carried by a massless particle. I mean, gravity is a gauge theory, so the carrier is a massless and is the graviton. I can do the exact same thing with electromagnetism, for example, but again, I can do this, I think, for a more exotic theory, but I have to consider massless particles, because there must be a well-defined low energy limit that corresponds to long range limit, and long range interaction are carried by massless particles. So I would say no. I mean, if the question is, can I replace the graviton with a massive particle? The answer is no.
Okay.
But because what theory will be that? I don't know. Will be some short range theory with no classical limit, maybe.
Okay, thank you.
Okay, please, Alan, go ahead with your questions.
Hi, Claudio. Thank you for your amazing talk. So, my question is, how can I observe the things that you are calculating? For example, in which kind of experiment or in which kind of process I can observe these things?
You mean the quadrupole?
Everything. I mean, I want to know all these kind of things you are calculating with these scattering amplitudes. Where can I observe the things you are calculating? I mean, I want to know in the experimental part where we can observe. this kind of things?
Yeah, the short answer is that there is no experimental part because we are working in arbitrary dimension. So basically, in 4 dimensions, the things are well known, I would say. So we know what is a Kerr black hole and what is not. But I mean, the new stuff here is in arbitrary dimension. So I mean, in 5 dimensions we have new stuff, but I mean, we apparently live in a universe with 4 dimensions. So I would say that there is no experimental things here. Yeah, because yeah, I mean, because of course the multiple moments of a space-time can be probed experimentally. So, for example, there are ways in which also through gravitational waves we can extract the quadruple moment, which is the leading one of a source, and we can test if that quadruple moment is the quadruple moment of a black hole. So if we think that we are observing a gravitational wave emission of 2 black holes, the quadruple moments of the source must be the one of Kerr. So we can test we can test that. But in 4 dimension is everything is almost well known. So here the new stuff is in higher dimension, and of course there are no experimental counterpart. The only thing that come to my mind is that maybe related also to the one of the first question is that what happens if I consider these arbitrary dimension metrics? For example, I take the metric in 5 dimension and I make a dimension reduction. So for example, I compactify 1 dimension and I obtain a solution with which is now live in 4 dimension. And maybe that solution that now is a solution in 4 dimension has some particular property. So this is the only thing that pops to my mind. But yeah, that's it.
Okay, thank you so much.
More questions? If there's no more question, well, we thank again to Claudio for this amazing talk.
Thank you very much.
Thank you, Claudio. Thank you very much.
Thank you, Jonathan. Bye.
Thank you for
everyone.
accepting.
Pues